Introducing dopant impurities to change the electrical properties of a semiconductor is a process known as doping. The integrated circuits that make modern electronic devices possible are fabricated from semiconductor materials, primarily silicon. Silicon, typically processed into a wafer, acts as the substrate upon which the circuit is fabricated. At the atomic level, the material exhibits a highly ordered arrangement of atoms referred to as a crystalline lattice. A semiconductor material, such as silicon, can conduct electricity depending on the conditions it is in. At room temperature, it has very few free electrons that can move and create an electric current. The electrons in the outer shells are occupied, forming bonds with neighbouring atoms, keeping them bound to the crystal. To fabricate transistors, we need to increase the conductivity of silicon in a controlled way. One way to do that is by adding atoms that contribute free-moving electrons. Phosphorus is a good example, because it has one more electron than silicon in its outer shell. That extra electron can't form a bond with any neighbouring atom, so it's free to move through the material, allowing an electric current to flow. When silicon is modified with an excess of free electrons, it's called an N-type semiconductor, since electrons carry a negative charge. We can also add impurity atoms that have one less outer electron than silicon, such as boron. In this case, one of the bonds remains incomplete and can be filled by an electron from a neighbouring bond. When that happens, the silicon atom that gives up the electron is left with a positive charge. We call this absence of an electron a hole. Free holes also move through the material and contribute to the electric current. When silicon contains an excess of holes, we call it a p-type semiconductor because holes behave like positive charges. The atoms we add are known as impurities, since they make the material no longer pure silicon. After doping, there is about one dopant atom for every 1,000 silicon atoms. But how do we actually introduce these impurities into semiconductors? Doping is one more processing step in the fabrication of electronic devices and is carried out inside a clean room, which is an environment with controlled conditions and extremely low levels of particles. The most common technique is called ion implantation. In most cases, we only dope a specific region of the material. To do this, we first grow a silicon dioxide layer that acts as a barrier. Then, using photolithography, we open a window in that layer to expose only the area we want to dope. Here we introduce new atoms into the crystalline lattice by accelerating electrically charged atoms, that is, ions, toward the silicon surface so they can be implanted. The ions travel like high-speed projectiles, and when they hit the crystalline surface, they penetrate the material, enter the lattice, and change its electrical properties. The process takes place in an ion implanter, which is made up of different sections, all under vacuum, where the ions travel from the ion source through the ion selector, then through the accelerator tube, the focusing system, and the scanner, until they reach the process chamber, where the wafer is located. The process begins by introducing a gas that contains the element we want to implant into the silicon. The electrons emitted by a filament collide with the gas molecules, generating different types of ions, which we can later extract from the source by applying an extraction voltage. Once the ions exit the source, they pass through a curved region under a strong magnetic field. The field bends their paths differently, making it possible to filter out unwanted ions and keep only the desired ones. In the accelerator tube, a series of rings generate electric fields that accelerate the ions to high speed. The accelerated ion beam then strikes the wafer placed in the implantation chamber. The result is an implanted area roughly the size of a fingerprint. So to implant larger areas, a scanner is used to deflect the ion beam across the surface. During implantation, a current sensor monitors in real time how many ions have been implanted. This makes it possible to determine when the desired dose has been reached. Another technique is thermal doping, which is a diffusion process. At high temperatures, atoms or molecules naturally move from regions of high concentration to regions of low concentration. In this case, we take advantage of this behavior to modify the electrical properties of the device. Again, by combining it with other photolithography and deposition processes, it is possible to selectively create regions doped with impurities. In the first stage, the dopant gas is injected into the process chamber. It moves toward the surface of the region to be doped. In the second stage, the dopant is driven deeper into the silicon thanks to the increased temperature. The dopant diffuses isotropically, meaning it spreads the same way in all directions. Once the wafer has been doped, we can move on to the next step in the chip fabrication process.